The term ambient intelligence means that smart environments react to the presence and activities of people and objects and offer them corresponding services. The technology fades into the background and is ideally not obvious. Initial research on smart cities was essentially limited to technological feasibilities. However, research in this area has evolved to a socio-technical perspective. A major criticism of previous implementations is the lack of participation and inclusion of all citizens. However, the requirements for smart environments are not the same for all people. It is important to address the individual needs of citizens and especially to let disadvantaged people benefit from it. According to the World Health Organization, the proportion of people with disabilities is about 15%, that is more than 1 billion people. The Smart City Charta defines guidelines for future smart cities. These should sometimes be participatory and inclusive. The digital transformation should include people with impairments of all kinds. In order to be able to support people with special needs, it is crucial to be able to differentiate between groups of people. Therefore, we demonstrate a prototype for a camera-based system that allows automated differentiation between different groups of people. Based on a new building of the Nuremberg Institute of Technology, we outline a prototype for an information center that recognizes different user groups at the entrance of the library and offers individual support. For better planability and independence from material and regulatory restrictions, for example the ongoing COVID-19 pandemic, we use a VR simulation, which proved to be very useful. After entering the library, a camera detects the person and recognizes which group of people the visitor belongs to using pre-trained machine learning components. For our initial prototype, we consider 3 exemplary groups of people for simplification purposes. First, visitors who are pedestrians. Second, visitors who use white canes, and third, visitors who use wheelchairs. The classification artifact is then sent via Bluetooth to a microcontroller. This controller then triggers the movement of a table with a tablet containing audio-visual information so that wheelchair users, for example, can operate this tablet at the appropriate height and inclination. If the person is a sighted pedestrian, so no white cane was detected, the table is moved up and leveled, if necessary. In both cases, the table also draws attention to itself auditively. If, on the other hand, a person with a white cane was detected, the audio-tactile tablet on the second, fixed, table is activated and auditively draws attention to itself. Once there, via the floor indicators for white cane usage, the blind user receives explanations on how to use the tablet with a text document written in Braille. With both tablets, users can select a destination, for example, a specific book or area of the library, and are shown visually or tactilely how to get there. The route is not only presented to the user in a variable way via the modality of output, but also adapts to the needs. Blind people, for example, often prefer the stairs to the elevator and therefore receive a corresponding route. For other people with limited mobility, such as wheelchair users or users of walkers, the use of the elevator is intentionally included in the route to the desired destination. Further optimization, development, also in the individual research fields of the modules, as well as an evaluation involving a comprehensive user study will be needed towards a deeper understanding and possible dissemination of such an ambient intelligence approach. But our contribution shows a first step to get there and seeks to stimulate further activities with the presented prototype.